These are the gas stoichiometry notes. Before we start these notes, if you can go ahead and do the warm-up, give that one a try. That should be a review of our ideal gas law. And then these notes are going to cover the first part of the gas stoichiometry notes, which is scenario 1. As we go through this warm-up, find the volume. So we are looking for volume of 1 mole of hydrogen gas. So N is 1 mole. At STP, well, standard temperature is 273 Kelvin, standard pressure is 101.3 kPa, and as we look at that ideal gas law, we still need R, but R is that gas constant. And so that is on our formula sheet, so you should be able to go ahead and grab that. And then as we go through, we can find volume, because we know all of our other 4 variables. When you go and plug that in, I get volume is going to equal nRT divided by P. I plugged in all my values, and I got out 22.4 liters. And so this is one thing, or one relationship, that we are going to be looking at as we start to look at gas stoichiometry. Because if we have standard temperature and pressure, that means this relationship is always going to exist. At standard temperature and pressure, 1 mole of gas is always going to have that volume of 22.4 liters. But if we are not at standard temperature and pressure, then that relationship doesn't exist. So looking at these notes and our little introduction here, we're back to working with stoichiometry when we are looking at a stoichiometry problem. So we have a reaction, we're given an amount of one of our chemicals, and we're asked to find, well, how much would that mean we need of another chemical in that reaction? We need to consider the 2 possible scenarios. The notes that we have are organized into those 2 sections to represent those 2 possibilities, and then we have examples as well. We're going to start, and just in this video, I'm going to cover scenario 1. And scenario 1 is if our reaction is taking place at STP, standard temperature and standard pressure. So if we know both of those things, then we are going to always know this relationship. 1 mole is 22.4 liters. And so that's going to kind of join our other relationships we have. We know that 1 mole equals molar mass in grams for any given chemical. We also know that 1 mole is 6.022 times 10 to the 23rd molecules. That's that Avogadro's number. We don't use that one as much because we can't measure it in a lab, so we've most often been using the grams. But now when we are at STP, we will have another mole ratio that we can use. And so we know that 1 mole will always equal or occupy a volume of 22.4 liters. And so that becomes at one of those constants. And so we can add that to these 3 mole conversions we have along with our mole ratios if we want to solve a problem where we have something at standard temperature and pressure. I went ahead and wrote out our reaction for us. Hydrogen gas and lithium hydroxide are produced, so those are my products, when lithium metal is added to liquid water. What mass of lithium metal is needed to produce 35 milliliters of hydrogen gas at standard temperature and pressure? One note for this, though, is that 1 mole equaling 22.4 liters is only for chemicals that are in the gas state. And so the only time we would ever be able to use that in this first example is on that hydrogen. But we can use that when we're looking at those hydrogen relationships. Anything that's going to have a different state of matter is not a gas, so it's not going to behave that way. And so for this problem, we'll only be able to use that 1 mole of H2 is going to equal 22.4 liters of H2 because that is gas. As we look at this problem and what we have, what mass of the lithium metal, and so we are looking for mass, grams of lithium, is needed to produce 35 milliliters of hydrogen gas. We have 35.00, nope, just 10 milliliters. Our standard unit, though, for volume is liters, and so we are going to need to, 1,000 milliliters is 1 liter, divide by 1,000, and so let's convert that, and we get 0.0350 liters of hydrogen gas. And so as we go through now, we can do that stoichiometry. We know a liter to mole relationship, so then once we get to moles, we can change to moles of lithium. As we look at that, I'm going to have my starting value, 0.0350 liters of hydrogen. I need to get rid of liters of hydrogen, and because this is at STP, I know that 22.4 liters of hydrogen is going to be 1 mole of hydrogen. Now I want to cancel my moles of hydrogen. I want, now that I'm at moles, I'm going to change from my moles of hydrogen to what my problem asked me for. So to my moles of lithium. So getting rid of my moles of hydrogen, getting to my moles of lithium, and we see that we have 2 moles of lithium to 1 mole of hydrogen. And now we can get to the grams of lithium using molar mass. We know to get rid of moles of lithium, 1 mole of lithium is molar mass. I can go to my periodic table. 6.94 grams of lithium are in 1 mole, and I can go ahead and do my calculations. Remember, we're going to multiply all of our values in the numerator. We're going to divide by any values in the denominator. We set this up so that my liters of hydrogen canceled, my moles of hydrogen canceled, canceling just those units, moles of lithium. So we're left with grams of lithium, and I get 0.216875. Let's look at our sig figs. 3 sig figs from that 35.0, 3 sig figs from our 22.4. Our mole ratio does not have sig figs. Our molar mass of lithium has 3 sig figs. So we're going to keep 1, 2, 3. We're going to need to round that 6 up though, 0.217. We need a unit, grams, and we need to say what chemical we have. So if we have that at STP, that means we can do this just as a multi-step stoichiometry problem. I've got the reaction for the next one written out. If you want, go ahead and give that one a try on your own, writing out the reaction and then come back and check. Things we want to remember are diatomic elements, especially when we're working with gases. A lot of those nonmetals are diatomic. All right, so hydrogen gas and oxygen gas combine to form water vapor. Vapor means gas. And so as we look at these, all of these are gases, and so we can treat all of them as gases using what we've talked about this unit. How many liters of water, so we are looking for liters of H2O, can be made from 34 grams of oxygen at STP. So we're at that standard temperature and pressure, which means we can use that 1 mole equals 22.4 liters. And because this has only gases in the problem, we could use it on any of these chemicals, but let's look at what our problem is asking us. So we have 34 grams of my oxygen. I want liters of water, so I need to get rid of grams of oxygen. I know 1 mole of oxygen is that molar mass. So we can go to our periodic table. That's diatomic, and so we do need to go 15.999 times 2, so 31.998 grams of oxygen. I'm at moles, so now I need to use my mole ratio, moles of oxygen to moles of, my problem is asking me for water, H2O, and I'm going to, 2 moles of H2O and 1 mole of O2 from that coefficient. We need to make sure our reactions are balanced so we have the correct mole ratio. And now I am able to use, because of that at STP, that 1 mole of this H2O gas is going to have a volume of 22.4 liters of H2O gas in order to get the answer I am looking for. Go ahead and plugging that in our calculator. Remember, we are multiplying anything in the numerator and then we divide by everything in the denominator. I got 47.6, and let's look at our sig figs. We've got 2 sig figs from my given, 5 sig figs in that molar mass. Our mole ratio doesn't have sig figs, and 3 sig figs in that conversion factor. So 2 sig figs is our least amount of sig figs, so we're going to round to the nearest 1 whole number. And so that means that 47.6 is going to round up to 48. We need to include units, liters of H2O, and what our chemical is. So if we recognize a problem is at STP, we can use this as a shortcut. This only is going to work at STP. When we talk about scenario 2 in the next video, that's going to be something you can use if you are at STP or if you are not. Reach out to your teacher with any questions on this first set of notes.